Okay, so yeah, the idea is to try to measure experimentally this diagram. And yesterday I told you that whatever the probe that we use to, let's say, access the behavior of the phonons within the solid, the idea is to have this probe with a value of this particle with the given energy, given momentum, and then see how the energy and momentum, sorry, I'm out of the board. Just then the idea is just to see what happens to the energy and to the momentum of the particle after the that particle has interacted with the phonons in the solid. So to have the opportunity to interact with the phonons, the idea is to find a particle that is able to interact with the ions, but not with the electrons. Because in this case, the idea is just to couple this external particle with with just the ionic oscillations. So in general, what is used for this kind of measurement, in general, people use two kinds of particles, photons or neutrons. In the case, let's say, which is the best for these guys, one has to make reference to the energy conservation. So the energy of the particle after the interaction is equal to the energy of the particle before the interaction, plus or minus, depending on the absorption, plus sign, or the emission, minus sign of a phonon has taken place. And also P prime, that is the momentum of this particle, is equal to the momentum of the particle before the interaction. Then we have plus or minus h bar k, depending on, again, on the absorption or the emission of a phonon. And then we have plus g, because the interaction takes place within the ionic lattice. So the crystal momentum is conserved within a value, an arbitrary vector g belonging to the reciprocal lattice. So if those two constraints have to be fulfilled, then the idea is to find a particle where both E and P are of the same order of magnitude of the energy and the crystal momentum of a phonon. So in that case, the particle that we use to interact with the phonons have energy and wave vector that are comparable with the corresponding quantities for phonons. So in this way, we may better appreciate what happens, what happens when that particle interacts with the phonon. Now, what happens if we see what are the features in case we use photons? In case of photons, we have, so for photons, we have that the energy is equal to the Planck constant times the frequency. And in this case, we have that the Planck, the Planck constant, we may write that as C divided by lambda. And if we multiply and divide by so if we write h as h bar times 2 pi, and 2 pi over lambda is the wave vector corresponding to the phonon, then sorry, today nothing is working fine. Okay. let's start back from the beginning. And just a moment, I've lost the point. No, the idea, sorry. I've lost it. If k is 2 pi over lambda, then we may replace, so 1 over lambda is k divided by 2 pi. Yeah, so the point is that, so from k we refer to lambda, and in this case, the idea was to include here a value of k that is of the order of the k values that we have for the phonons. So in general, the k values that we use for phonons are of the order of pi divided by a. So in this case, we have h c divided by 2 pi, and then we have pi divided by a. So yeah, that was the point. So in case we substitute here a of the order of 3 angstroms, then what we have is that the energy of this phonon, the energy of this photon is of the order of 6 times 10 to the power of 2 eV. So the comment in this case is that for photons, in case you consider photons, then you may have a photon that has the same momentum of the wave vector of a phonon, but in this case, if you fix that constraint, then the energy of the photon is larger and larger with respect to the typical energy of a phonon. So in this case, the problem is that the photons may have the right wave vector to properly interact with the phonons, but in that case, their energy is so high with respect to the typical phonon energy that is difficult to, let's say, access experimentally a variation of the order of tens of millieV over an energy that is of the order of hundreds of eV. So from this point of view, we have an experimental problem from the experimental point of view. So it's difficult to access a variation of energy of this order of magnitude over an energy value that is so high. So let's say due to that, the photons are not in general the main probes used for to access or to interact with phonons. So in general, one tries to make resort to neutrons. So in case we consider neutrons, in this case, they have no charge. So once you are able to have a neutron traveling in space, then the energy of that neutron is mainly kinetic. So the energy is p squared divided by twice the mass of the neutron. So at this point, if we replace p with h bar k, and we use as an estimate of k, again, pi divided by a. So here we have 1 divided by 2m, then we have h bar, and pi divided by a as an estimate of the size of the wave vector of the phonon, or the equivalent momentum of the neutron, such that the momentum of the neutron is equivalent to that of the phonon. Then here we have an energy for the neutron that is of the order of 40 millieV. So in this case, we have the opportunity to have a particle that is from both from the point of view of the energy and from the point of view of the wave vector, quite close to the phonon. So that's why neutrons are one of the main probes that are used to detect the behavior of phonons. Just a comment about neutrons. In general, neutrons are not charged particles, so due to that, you may not accelerate a neutron. So if you want to, let's say, send this, so let's suppose that this particle here is a neutron. If you want to send a neutron against your solid, due to the fact that, again, it has no charge, you may not accelerate the neutron to the energy, to the desired energy. So what is generally done is that you take those neutrons from the decay of a radioactive element. Due to in general, the energy that you have after the decay is not 40 milliV, but is 10 to the power of 6 eV. So the energy, the starting energy of the neutron after the decay is larger and larger with respect to those 40 milliV. So what is done is to, let's say, after the decay, let the neutron interact with the medium where the neutron may thermalize and slow down. So at that point, the neutron may have an energy that is comparable to some tens of milliV, and at that point you may use that for the experiment. I hope in Italian you would say that you thermalize the neutron using acqua pesante. So you enrich the let's say you change the isotope of hydrogen within the water, so to increase the number of neutrons you have within that isotope, and in this way you have a kind of water that strongly interacts with the neutron and slow that down up to the final point where the neutron has an energy that is of the order of thermal energy, because thermal energy is 25 milliV, so it's close to, again, some tens of milliV. So in general, for these experiments, you use a lab where you may have radioactive elements and that are used to produce the neutrons that then are sent to the solid for the experiment. So in this case, we have that E prime is the final energy for the neutron. So now we focus on neutrons. And again, P prime is P plus or minus H bar K plus G. So let's try to see which kind of information is it possible to extract from this kind of measurement. And if we use this second equation, this tells us that P prime minus P is equal to plus or minus H bar K plus G. And if we, sorry, I forgot the H bar close to the reciprocal lattice vector. If we divide by H bar, then we have that P prime minus P divided by H bar is equal to plus or minus K plus G. We may take G on the other side of this equation, so we have that plus or minus K is equal to P prime minus P divided by H bar minus G. So at this point, we have an expression for K, and K is the wave vector that corresponds to the phonon that is interacting with the neutron. So we may use this K and substitute this value within this equation where we have the energy conservation. So concerning neutrons, energy conservation means that P prime squared, so the energy after the interaction divided by twice the mass of the neutron minus P squared divided by twice the mass of the neutron, so final energy minus initial energy is equal to plus or minus H bar omega s of K. So if we use this equation and we insert the value of k here, we have that we may drop the plus or minus, because the what we expect, as we see from this diagram up here, the phonon dispersion is symmetrical with respect to the origin. So plus k and minus k gives exactly the same value of the frequency. So if we replace this expression, we have that p prime squared divided by twice the mass minus p squared divided by twice the mass is equal to plus or minus h bar omega s of p prime minus p divided by h bar. Then we should in principle write minus g, but we know that omega is periodical and has the same periodicity of the reciprocal lattice. So due to that, we may also drop the minus g term. So in this case, we have just p prime squared divided by twice the mass minus p squared divided by twice the mass is equal to plus or minus h bar omega s p prime minus p divided by h bar. So at this point, we may build up a diagram in this way. So p prime minus p are features that we may access experimentally, because p prime, as represented here, is the momentum of the neutron after the interaction, and momentum and energy are strongly related due to the fact that the energy is the square of the momentum. The idea is, if you have the initial neutron, so you know both E and P, then you have the interaction with the solid, the neutron after the interaction. So as P is a vector, P it has initially this direction. Then for what concerns the final value of P prime, we know what is the orientation of P prime with respect to P, because we know what is the point where the neutron interacts with the detector. So the detector in general for neutrons is very large. So we have detectors all over here. So at this point, we may determine where the neutron impacts on the detector. So due to that, we know what is the direction of P. So we have a the opportunity to fix in a three-dimensional way the direction of P. Then when the detector measures the energy of the neutron, we have the opportunity to obtain both the energy and the momentum, the modulus of the momentum. So using this kind of experiment, P prime minus P is detected by looking at the difference between the vector P and the vector P prime and vector P, and we may both measure the direction and modulus and the orientation of those two vectors. Then P prime squared is the energy after the interaction that can be measured by the detector. P squared divided by twice the mass is the initial energy. So we know that because the beam of neutrons is produced, and so you know what is the initial energy for the neutrons. So due to that, you may use P prime minus P divided by H bar to fix one point here. So this is P prime minus P divided by H bar. And then you may plot on the vertical axis the corresponding value of E prime minus E. So at the intersection between those 2 points, you fix the value of the frequency, because E prime minus E, apart from the H bar coefficient, is exactly or we may plot directly here h bar omega. So a prime minus c gives you exactly the value of the energy of a phonon, and the horizontal position of that value can be extracted by p prime minus p. So in this way, it is possible to reconstruct the full dependence of the dispersion curve. In particular, how may we distinguish one branch from another branch? Concerning the branches are situations or represent a situation where for a fixed value of p prime minus p divided by h bar, you expect to find different values for the phonon energy. So the idea is that if you have a look at the, let's say, at the result of the, the signal that you measure at the detector that is represented here. So if you have a look at the energy of the neutrons that are revealed by detector that is in this position, what you find is that if you plot the energy of the neutron, maybe is it not written correctly, but this is in, I rewrite that, this is E. So if you plot the energy of the neutron after the interaction, and here you plot the number of neutrons that appear for a fixed value of the energy, in case you have different branches, you may have, for instance, different peaks. So you have for a fixed geometry, that means for a fixed orientation of p prime, you may have 3 different peaks, or let's say a number of peaks that ranges from 1 up to 3, depending. So you have just one peak if you have full degeneracy of the branches, or 3 different peaks in case the energy corresponding to the energy values corresponding to the different branches are not exactly the same, are different with respect to different with each other. So in this case, if you find 3 peaks, for instance, you may plot here the 3 different values. So at this point, if you do that for all the possible values of p prime minus p, you may build up the full dependence of the energy of the neutron as a function of the wave vector. This is the diagram just for acoustic phonons. So in case you have also optical phonons, you will have additional peaks that are related to the presence of the optical branches that are up here. So in case you have both acoustical and optical, you will observe additional peaks in the diagram. So in this case, again, you may reconstruct the phonon band structure just by, again, letting the neutrons interact with your solid and looking at what happens to the neutrons for all the possible angles that you may access using your detector. So in this case, you have the opportunity to probe many values of p prime minus p, and let's say this difference depends on the angular sensitivity of the detector, and for any angular orientation, so for any angular position, then if you measure the energy of the neutron, you have the dispersion of the neutron band, of the phonon band. And say so this is in general what is done experimentally, and And this is the way that is used for, again, to access phonon dispersion. And so the main source, the main kind of particle that is used to describe the phonon dispersion are neutrons. But just as a general information, now I changed page. Just as a general information, I told you that before, if we just to conclude this part, have a look again to the photons. What I told you before, if a photon has a momentum that is similar to the phonon momentum, then the energy of the photon is larger and larger with respect to the energy of the phonon. So due to that, it's impossible, let's say not impossible, but it's very difficult to detect the interaction between the photon and the phonon, because the change in energy of the photon is very small with respect to the absolute value of the photon energy. Due to that, and in this case, the main problem is that you have not the experimental opportunity to detect such a slight variation of energy over an X-ray. So the main problem is that concerning X-rays, we have not the experimental resolution to detect such a very small variation over the energy of the X-ray. But if you for a while, let's say, neglect X-rays and concentrate on, so if we use these, so if we use visible light photons, in this case, the typical energy is of the order of 2-4 eV. So this is larger than, again, the typical 10 milli eV energy that we have for phonons. But in the visible light range, we have an experimental resolution that is able to detect this small variation of the energy with respect to the initial energy of the photon. So due to the fact that here, due to all the interferometric techniques, we may detect this small variation of the energy of the photon, due to the interaction with the phonon, then we have the opportunity to apply visible light spectroscopy to access the features of the phonons. What is the drawback? So we have the resolution to detect the change in energy. So the energy of the photon after the interaction So we have the resolution to access the energy change due to the interaction with the phonon, but concerning the concerning momentum conservation, the crystal momentum conservation, what we have here is that if we have photons in the visible light range, we have already seen that this P is nearly zero for what concerns the scale that is used to describe phonons, because phonons have a wave vector that is of the order of pi divided by a, where a is the lattice spacing, while visible light photons have a wave vector that is of the order of pi divided by lambda, and lambda is the wavelength of the photon. So in this case, the let's say P is nearly zero on the scale of the phonon wave vectors. So if we want to fulfill the second equation, we may do that, but only for k values that are close to 0. So the point is that if we use visible light to access phonons, we may investigate just the we may investigate just the central part So using visible light, just the central part of this diagram may be investigated because the exchange wave vector of the phonon has to be very, very small such that the photon may interact with that phonon. So if K is large, then it's impossible for the photon to fulfill this crystal momentum conservation law. So we may just access the phonons that are close to the center of the zone. And in this case, it's possible to distinguish two kinds of spectroscopies. One spectroscopy is called the Raman spectroscopy, and the Raman spectroscopy is able to access optical phonons. So if you remember, optical phonons have the opportunity to display counterphase oscillations in between atoms belonging to the so if you have more than one ion, if you have a basis with more than one ion, then within the basis you have the opportunity to observe counterphase oscillations. So if you have counterphase oscillations, in general you have a variation of the dipole moment of the system. So thanks to this variation of the dipole moment of the system itself may couple with the electromagnetic waves. So in this case, you have a coupling between electromagnetic waves and visible light. And the investigation of this part is called Raman spectroscopy. So with Raman spectroscopy, in general, you access optical phonons. There is also another spectroscopy that is devoted to acoustic phonons, and that spectroscopy is called Brillouin Spectroscopy. And Brillouin Spectroscopy is able to access acoustic phonons. In case of acoustic phonons, the oscillation is not counterphase, is in phase. So in general, and in particular for acoustic phonons, whose K is very low, as we have here, you expect to have no change in the dipole moment. So what is the physical motivation that allows light to couple with the system, even if you do not have a change in the dipole moment? You may understand that if you consider that phonons that are very close to the center of the zone, let's say acoustic phonons that are very close to the center of the zone, have a wavelength of oscillation that is very large. So in this case, the lambda, the wavelength of the phonon, is larger and larger with respect to the typical scales of the solid. If you have this kind of oscillation, you may have a sort of, if you think about an acoustic wave, in an acoustic wave, you have, let's say, regions where you have a compression of the system and regions where you have, if you have a compression, you have an increase of the density, and regions where you have an increase in size of the system. So in that case, you have a decrease of the density. So those long wavelength phonons produce a change in density, in the density of the solid. So you have an oscillation of the density that is in phase with the oscillation of the phonon, with the propagation of the phonon. So in this case, you may couple light may detect this change of density because the change of density is somehow, let's say, may give rise to a sort of change in the index of refraction. So you have a slight change of density, a slight change in the index of refraction, and the light is able to detect this slight change. And as you may imagine, for Raman spectroscopy, you have a detect energies that are, let's say, the largest possible energies that you have for phonons. Differently, for Brillouin spectroscopy, you have an energy of the phonon that is very close to zero. So it's more difficult to, let's say, apply the Brillouin spectroscopy, and it's slightly easier to apply Raman spectroscopy. So Raman spectroscopy was the first one to be developed. Then when the capability of the labs to use interferometric techniques to access lower and lower energy variations for the photons, then in that case, it was also possible to develop Brillouin spectroscopy. So both allows you to access phonons. In one case, in the case of Raman spectroscopy, you access optical phonons, and in the case of the Brillouin spectroscopy, you access acoustic phonons. Okay, so this was, again, not a full detail, not a full description of the two spectroscopies, but I included this comment just to let you know that it's clear that the neutrons have a better energy momentum relationship, so they are easier to be coupled with phonons, but also visible light may be used to access partial details concerning the phonon dispersion, even if the neutrons is not the best one to couple those with the phonons. And in this case, you have the opportunity to use two different spectroscopies, the Raman one and the Brillouin one. Okay, and as I, even if this first part of the lesson was not, even if there were some problems, I prefer to stop here now, since in the last thing that I would like to present you concerning phonons was the part regarding their interaction, the contribution of the phonons to the dielectric constant, to the permittivity of a solid. Here the calculation is a bit long, so the full description is a bit long, so I prefer to make a short break now and then to go on with this topic after the break. Do you have comments or questions?